section 1.5, and we're going to talk about a homogeneous system, AX equals 0, and how it's related to the non-homogeneous system, AX equals B. Let's start with a little review. You might want to pause the video and see if you can do these 3 problems on your own, and then start it up. All right, so hopefully you did that. If somebody at the Aubrey feed store gives you a vector B and asks you to write it as a linear combination of U, V, and W, and you reduce the augmented matrix and come up with this, you're going to tell the person that B is equal to negative 2U plus 3V, because these are the weights in that linear combination. So you've got 0 W's. So that's what you would tell the person. Then you head off to ACE, and someone else gives you X, Y, Z and asks you to write B as a linear combination of X, Y, Z. You do a quick matrix reduction and you come up with this matrix. You're going to tell the person that B is not a linear combination of X, Y, and Z, so it can't be done, because this corresponds to an inconsistent system because we've got a row that goes 0 equals 1. All right, finish the theorem. This is theorem 4 from last time, which you're going to have to memorize. The following are equivalent. AX equals B is consistent for all B. That's equivalent to A has a pivot in every row. So we're going to have some theorems that talk about pivots in columns. This theorem talks about pivots in rows. For every B in Rm, B is a linear combination of the columns of A. And finally, that's equivalent to the columns of A span Rm. And that's A is an M by N matrix. And we'll refer to this theorem later in the lecture today. All right, a homogeneous linear system has the form AX equals 0. So homogeneous is one of those overused words in math, but in this context, it means a linear system of the form AX equals 0. These are just little jokes. You fit in nicely because this is a homogeneous population, means everyone's the same. And in milk, we don't say homogeneous, we say the milk is homogeneous, meaning you've taken the fat off the top and then it kind of all looks the same. Okay, a homogeneous linear system looks like this, but sometimes we get a little bit lazy with our just writing equation in short form and we forget what dimensions these things are in. Where is 0 from and where is X from? Rn or Rm? So we can just do a simple example. Suppose we have the matrix 1, 2, 3, 4, 5, 6. And we're going to multiply by a vector, x1, x2, x3, and we would come up with another vector. If this matrix here is 2 by 3, this vector is 3 by 1, and so when we multiply, we'll end up with a 2 by 1. So the 0 here refers to a vector in Rm. M is 2 in this example, and the X refers to a vector in Rn, N is 3 in this example. So an important fact, 2 important facts, AX equals 0 is always consistent. And the reason for that is that X equals 0 is a solution. And that's because A times 0 is always going to be 0. So you'll always have at least one solution, and that's the trivial solution. We call that the trivial solution, X equals 0. That means all the entries are 0. So we have a non-trivial solution, meaning at least one entry is not 0, if and only if the system has at least one free variable. And that's because if there are no free variables, then the unique solution is the trivial solution, X equals 0. All right, this is example 1 from your text. We're looking at the matrix. This is a homogeneous system, AX equals 0. And so I've reduced the augmented matrix here, and I filled in the twiddles on the bottom row. I want you to fill in the twiddles on the top row. You can do that on your own. Figure out what row operation I did at each step to get to the next matrix. Just want to point out one thing in that matrix reduction. I didn't start by turning this into a 1, okay? I could have, but I saw that negative 3 and 6 are multiples of 3. So instead of turning that into a 1 from the get-go, first I used that 3 to kill things below. And then at the very end, I introduced the fractions. I said, okay, now I got to bite the bullet and divide by 3. So it's good to wait to introduce fractions if you can. So now we're here. let's write down the solution to this system. We've got three variables, x1, x2, x3. x1 corresponds to a pivot, x2 corresponds to a pivot, x3 does not. So x3 is free. We start at the bottom. x3 is t, x2 is 0. That's what the second line reads. And x1, if I read that top line, x1 is 4/3 t. So my solutions look like x bar equal to t times 4/3, 0, 1. That's the vector. The 4/3, 0, 1 is the vector v that you see in the picture there. I can visualize this as a line through the origin parallel to v, because it's all multiples of v. Multiples of v are parallel to v. So now we want to talk about how this same system, if I switch the 0, 0, 0s to a b, how the solution of that system would be related to the solution of the homogeneous system. So before I talk about theorem 6, I just want to mention how we're going to think about vector addition. We're going to think about it as translation. So suppose I have two vectors p and v, and in this picture they're in R2. If we're adding p to multiples of v, that has the effect of taking this line, and it has the effect of taking that line and translating it up to this blue line that goes through p, but it's still parallel to v. And the reason for that is when I add tv to p, remember, you do the diagonal of the parallelogram. That would be this point here. That's p plus tv. It's going on this line here, parallel to v through p. All right, so now we're ready for theorem 6. Suppose ax equals b is consistent and you have a solution p. So that means ap is b. Then every other solution of ax equals b can be written in the form p plus vh, where vh is any solution of ax equals 0. So that means that ax equals b, those solutions, and the ax equals 0 solutions are parallel. So here's a picture. We got solutions of ax equals b. They're going to be a particular solution of ax equals b, that's p, and then any solution, v sub h, of ax equals 0. Here's why that is true. Suppose we take a, multiply by this purported solution w, p plus vh. According to the theorem, that should be a solution of ax equals b. Well, let's distribute. That's ap plus a v sub h. Now, by supposition, ap is b, because p is a solution to ax equals b. That means that ap is b. And avh is 0, because VH is a solution to AX equals 0. So we're doing no harm by adding on any VH, because A is going to kill it. So we get B. All right, so this is example 1 continued. This is the same coefficient matrix as up here, and we've just replaced the 0, 0, 0 with B, which is 7, -1, 4. And I've already done the matrix reduction. Instead of augmenting with 0, I augmented with b, and I end up with this. Okay, so I'm going to read off the solution. I'm going to start at the bottom. x3, that's free, so call it t. x2 is not free. x2 is 2. x1 is not free. It's -1. Remember, there's a dotted line here, and so think of that as the equals. -1 plus 4/3 t. So let's write our solution in parametric vector form. We get -1, 2, 0. Those are the constants. And then the coefficients of t are 4/3, 0, and 1. This is the v from above, and this is my p in the theorem. So this is a line through p parallel to v. Okay, so try this one. Pause the video and see how you do. Okay. Let's write this down except from the bottom up so it looks more like a vector. So x3 is t, x2 is -2 minus 5t, and x1 is 8 plus 4t. So as in parametric vector form, okay, so our constants are 8, -2, and 0, and then multiples of t are 4, -5, and 1. This set can be visualized as line in R3 through what vector p and parallel to what vector v? This is your p, and this is your v. The next example is just to illustrate that the theorem on the previous page, was it theorem 6? Yeah, theorem 6 applies in R3 too. We're just going to go up a dimension. And so I've got an equation here, write the general solution of this non-homogeneous, think of this as a linear system, it's just got one equation in it, non-homogeneous linear system, write it in parametric vector form. How is it related to the solution set of the homogeneous linear system? So let's do the homogeneous first. So we'll jump down here. For the homogeneous linear system, I've got one equation, so I write down the augmented matrix. I don't have to reduce it because it's already reduced. So x3 is free, I called it T. x2 doesn't have a pivot, so that's free, that's S. And then x1 is 3s plus 2t. So I can write in parametric vector form the solution set of ax equals 0, the homogeneous system, like this. This, in the picture above, is the pink plane. All right, now let's jump up and look at the non-homogeneous. Again, we've got our matrix is already reduced, so let's start at the bottom. x3 is still free. x2 is still free, call that S. And x1 is now 7 plus 3s plus 2t. So our solution looks like the constants are 7, 0, 0, and then I'm going to have an s vector, and that's going to be the same as below, 3, 1, 0, and a t vector, and that's going to be 2, 0, 1. So this is the blue plane in that picture, all of this, blue plane. And it's the pink plane translated by this vector. This would be what we were calling P, by this vector P, 7, 0, 0. Just took the pink plane and translated it over. Okay, finally, what we're going to end with here is a question about pivots. And to answer these questions, I'm going to be looking at two things. Let's scroll back to page 1. I'm going to be looking at ax equals 0 has a non-trivial solution if and only if the system has a free variable. Okay, so there's one fact I'll be using. And then I'm also going to be looking at theorem 4, which talks about if A has a pivot in every row, that's equivalent to AX equals B is consistent for all B. So let's scroll down. We've got a 3 by 3 matrix. A is 3 by 3. It's got 3 pivots. Does AX equal 0 have a non-trivial solution? All right, if there's 3 pivots, that means the coefficient matrix has 3 pivots, there's 3 variables, that means there's no free variables. So the answer is no. No free vars. All right, and then the second question we want to ask for each of these is, does AX equal B have a solution for each B? The answer to this one is yes, because if we have a 3 by 3 matrix with 3 pivots, we're going to have a pivot in every row. Pivot in every row. So that's theorem 4. Okay, A is 4 by 4 with 3 pivots. Does AX equal 0 have a non-trivial solution? Yes, because there's going to be one free variable. You've got 3 pivots, but A is 4 by 4. There's 4 variables. One of them doesn't correspond to a pivot. So you have one free variable, okay? And then if we've got 3 pivots, does AX equal B have a solution for each B? No, because we can't have a pivot in every row. There's 4 rows, but only 3 pivots. So not a pivot in every row. Okay, A is 2 by 5 with 2 pivots. I always find it helpful to visualize these things. If A is 2 by 5, that means it's 2 rows and 5 columns. So it's wide and squat. So there's 2 pivots, bam, bam. All right, does AX equal 0 have a non-trivial solution? Yes. There's 5 columns. Each column corresponds to a variable, so there's 3 free variables. So this is a yes. 3 free variables. Does AX equal B have a solution for each B? Well, the answer there is yes also, because there's going to be a pivot in every row, because there's only 2 rows. If A is 3 by 2 with 2 pivots, so 3 by 2 is going to be skinny and tall. 3 rows, 2 columns, we've got 2 pivots. Does AX equal 0 have a non-trivial solution? No, because there are no free variables. There's only 2 columns but there's two pivots, so each column corresponds to a pivot column. So no. And then does AX equal B have a solution for each B? No, because we don't have a pivot in every row. We can't. There's 3 rows, but there's 2 pivots, so we've run out of space to get a pivot in that last row. Okay, and that's the end of this section.